Hi students, welcome to Methodology classes. In today's lecture, we are going to discuss exercise 1.3 of NCERT, class 10th mathematics. In this exercise, mainly we will be proving a given number as an irrational number. In class 9, we already have studied what are irrational numbers. We know what are irrational numbers, but in this exercise, we are going to learn how do we know that the given number is irrational. So, proving a given number as irrational, we will be using a theorem to prove that. So first of all, we are going to see what the theorem is, and after that, using that theorem, we will be solving questions from exercise 1.3 of class 10th NCERT book. So let us move to prove that theorem. So let us see what the theorem is. The theorem states that let P be a prime number if P divides A square, then P divides A, where A is a positive integer. So let us try to understand it. The proof is not in class 10, so we will just get a general idea of what this theorem is and what are its implications. So the theorem is saying that if P divides A square and A is a positive integer, so A is a positive integer, so by fundamental theorem of arithmetic, I can write it as P1 times P2 times P3 times Pn. And we can write it as, suppose power is x1, x2, x3 and xn. So this is the prime factorization of A, and this is unique apart from the order in which the prime numbers occurs. So what will be A square? So every power will become twice, so it will be P1 to the power 2x1 times P2 to the power 2x2 times P3 to the power 2x3 times Pn to the power 2xn. So I squared on both the sides, so the power 2 got multiplied with every power of the prime numbers. Now it is given that P divides A square. Now P is dividing A square means P is dividing P1 to the power 2x1 times P2 to the power 2x2 times P3 to the power 2x3 times Pn to the power 2xn. So P is dividing this, it means, and this will be possible only if P will be dividing one of the prime number P1, P2, P3 or Pn. If it is not possible for P to divide one of the prime number P1, P2, P3 or Pn, then P cannot divide A square because P1, P2, P3, Pn are all prime numbers. So suppose let P is equal to PR, where PR is a prime factor of A. A prime number can divide another prime number only if both the prime numbers are equal, otherwise it is not possible. So if P divides PR, where PR is a prime factor of A, so if P is dividing a factor of A, it means P will be dividing A also. So this was a general idea of the theorem. So this is what the theorem says, let P be a prime number, and if P divides A square, then P divides A, where A is a positive integer. So if any prime number divides the square of any given integer, positive integer, then that prime number will divide that integer also. So the next exercise 1.3 is totally based on this theorem only. So let us move to the exercise 1.3. So let us try to understand how we can prove that root 5 is irrational. In class 9th, we studied that root 5 is irrational because 5 is not a perfect square. So let us try to understand why it is irrational number. So we will prove it. So question number 1. Now we will prove it by using a beautiful concept that is called method of contradiction. So we are going to use method of contradiction. Now what is method of contradiction? In method of contradiction, whatever we need to prove, we assume the opposite of that is true. So now in this question 1, we have to prove that root 5 is irrational. So we will assume that root 5 is not irrational. So if it is not irrational, then it will be rational. So we will start as, let us take root 5 as rational. So if root 5 is irrational, so we know that any rational number can be written in the form of p by q. So we can write root 5 is equal to p by q, where p and q are integers and q is not equal to 0. So if root 5 is rational, then root 5 will be equal to p by q, where p and q are integers and q is not equal to 0. Also, p and q are co-prime. And if they are not co-prime, then we can make them co-prime by dividing both the numerator and denominator by their common factor. So we will assume here that p and q are co-prime, and this assumption is very important. This assumption is very important. We have to write this, otherwise our marks will get deducted. So we assumed that root 5 is irrational, and if it is a rational number, I can write it in the form of p by q, where p and q are integers. Now, if root 5 is equal to p by q, so I can write p is equal to root 5 times q. Now, squaring both sides, we can get p square is equal to square of root 5 is 5 times q square. Now we know that p and q are co-prime, so p and q doesn't have any common factor, so p square and q square will also not have any common factor. So from here, because p square is equal to 5 times q square, so I can say that 5 will divide p square. 5 divides p square. So if 5 divides p square, then 5 will divide p also by the above theorem. If 5 divides p, so I can write p is equal to 5r, where r is some integer. So we can put this p is equal to 5r in equation 1. So we can write from equation 1, we can say, we can replace p by 5r, so we will be, p square will become 25r square is equal to 5 times q square. Now I can cancel 25 by 5, so we got q square is equal to 5r square. Now q square is equal to 5r square, and r is a factor of p, and p and q already didn't have any common factor, so q and r also will not have a common factor. So if q and r doesn't have a common factor and q square is equal to 5r square, it means 5 divides q square. And if 5 divides q square, so I can say 5 divides q also. So this is equation number 2. So from equation 1 and 2, we get 5 divides p and 5 divides q. But our assumption was that p and q are co-prime, but 5 is a common factor of p and q. And why this happened? Because of our wrong assumption that root 5 is a rational number. So we can say, so root 5 is irrational. So this is the main method by which we prove any number as irrational. So let's quickly go through what we did in this. So the question was, to prove that root 5 is a irrational number, so we used the method of contradiction and we assumed that root 5 is irrational, and if root 5 is irrational, we can write it in the form of p by q, where p and q are integers and q is not equal to 0. Also, p and q are co-prime. So from here we cross multiplied, so we got p is equal to root 5q. We squared on both the sides, so we got p square is equal to 5 times q square. Now p and q are co-prime, so p square is equal to 5 times q square will be possible only if 5 divides p square. And if 5 divides p square, from the above theorem, we know that 5 will divide p also. And if 5 divides p, then I can write p as 5 times some integer. So p is equal to 5r. We substituted the value of this p in equation 1. So we got 25r square is equal to 5 times q square. We cancelled 5 on both the sides, so we got q square is equal to 5r square. Now again, r is a part of p, and p and q didn't have any common factor, so q and r will also not have a common factor, and q square is equal to 5 times r square. This will be possible only if 5 will divide q square. Now if 5 is dividing q square, then 5 will divide q also. From equation 1 and equation 2, we got that 5 is a common factor of p and q. But this is against our assumption that p and q are co-prime, and this result arises only of our wrong assumption that root 5 is a rational. So we can say that root 5 is an irrational number. Now let us move to the other question. Second one, prove that 3 plus 2 root 5 is irrational, and in this case it will be given that root 5 is irrational, because in class question number 1 we have already proved that root 5 is irrational. So using this result, we will prove that 3 plus 2 root 5 is irrational. So question number 2, we will be proving it in the same way as we did the first question. So let us assume that 3 plus 2 root 5 is a rational number. So we can write 3 plus 2 root 5 is equal to p by q, where p and q are co-prime, where p and q are co-prime, and q is not equal to 0. So from here we can say that 2 root 5 will be equal to p by q minus 3, and we can divide by 2 on both the sides, so we got root 5 is equal to p by q minus 3 by 2. Let us assume that this is equation 1. So we can see the right hand side is rational number, because p by q is a rational and 3 is also rational. So addition or subtraction of two rational number is a rational number, and 2 is also a rational, and specifically it is a non-zero rational number, and ratio of two rational number is again a rational number. So we can say that right hand side is a rational number, and left hand side root 5, we already proved in the first question, root 5 is irrational. And a rational number cannot be equal to an irrational number, so we can say this is not possible. And why it is not possible? Why we got such an equation? That is not possible because of our wrong assumption that 3 plus 2 root 5 is rational number. So we can say that, so 3 plus 2 root 5 is an irrational number. So this contradiction arises only because of our wrong assumption that 3 plus 2 root 5 is rational. So we will use the same method to prove any given number as irrational number. So these were the questions from exercise 1.3 NCERT. You can try the other parts of question number 3 similarly as we did the question number 1 and 2. In each case, we have to just bring a contradiction, and in the beginning we will be assuming them as a rational, and because of that assumption we will be getting a fundamentally wrong result, and using that we can say that we got this wrong result only because of our wrong assumption. So the given numbers are irrational. So I hope it would be clear to you. Now let us analyze some decimal numbers and try to convert them in the form of p by q. Try to analyze the denominators of those rational numbers. Let us take a decimal number 0.375. After the decimal place there are 3 digits, so we can write it 375, and there are 3 digits, so I can place 3 zeros in the denominator. Now both numerator and denominator have 5 or 0 at their units place, so we can cancel it by 5. So 5 7s are 35 and 5 5s are 25, and we can cancel it 200 times. So again we can cancel by 5. So 15 and 40, again 3 and 8. So we can say this is equivalent to 3 by 8. Now 8 can be prime factorized as 2q. Now let us take another decimal number, that is 0.104. Again we can write it as 104 by 1000 by the same reasoning as we did above. Now again both are even numbers, so we can cancel it by 2. So 52 and 500, again by 2, so 26 and 250, again by 2, so 13 and 125. 13 is a prime number and 125 is also 5q. So I can write it as 13 by 125, and 125 is 5q, so which can be written as 13 by 5q. Now we can take other numbers like 0.0875. Now 875 by, there are 4 digits on the right hand side of the decimal place, so we have to place 4 zeros. So 5 1 is 5, 3 37, 5 7 is 35, and 5 5 is 25, and we can have 5 2 is 10 and 3 zeros. We can cancel by 25, so 25 7 is 175 and 25 8 is 200. So which can be written as 7 by 80, and 80 is 16 into 5 and 16 is 2 raised to the power 4 into 5. So 7 by 80, that is 7 by 2 to the power 4 times 5. So by the conversion of these decimal numbers in the form of the fraction, we can see that there is a particular thing about the denominators in these fractions. Here, in case of 0.375, the denominator has only 2's in the denominator, and in case of 0.104, the denominator has 5q, only 5's are there, and in case of 0.0875, the denominator has a combination of 2 and 5 both. And all these decimal numbers are terminating, means they are ending after some digits on the right hand side of the decimal place. So this is not just in the case of these denominators, these terminating decimal numbers. This is true for every terminating decimal number. So on the basis of this, there is a theorem. We can see the theorem states that let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 to the power n times 5 to the power n, where n, m are non-negative integers. So every terminating decimal number can be expressed in the form of p by q, and what should be the form of q? Q should be of the form 2 to the power n times 5 to the power m, where n, m are non-negative integers. So as I have discussed earlier also, non-negative integers and negative integers, there is a difference between them. Non-negative integers means it starts with 0, it should not be negative. So 0 is not a negative, and it can be positive because it should not be negative. So 0, 1, 2, 3. So 0 will also be considered in this case. So whenever there is a terminating decimal number, we can always write it in the form of p by q, and the prime factorization of q should be of the form 2 to the power n times 5 to the power m. So this is the first theorem before the exercise 1.4. Now let us move in the opposite way. Let us take the fractions 3 by 8, 8, 13 by 125, 7 by 80. Let us try to analyze what will be the decimal expansion of these numbers. So 3 by 8, I have to convert it into decimal number, so we can write it as 3 by 2 cube because 8 is 2 cube. And to convert it into decimal, I want to convert the denominator in terms of powers of 10. So 2 cube is already there, I can multiply by 5 cube in the numerator and denominator. So numerator will become 125 into 3, 375, and 2 cube into 5 cube is 1000. So 1000, there are 3 zeros on the right side, on the rightmost places, so I can write it as 0.375. Similarly, the next one, 13 by 125, 125 is 5 cube. Again, to convert it in the power of 10, I can multiply by 2 cube in the numerator and denominator. So 13 into 8 is 104 divided by 1000, so that will be 0.104. Now 7 by 80, so 80 is 16 into 5, so 2 to the power 4, 16 into 5. Now I have to convert it in the power of 10 to convert it into decimals. So 5 is there and I want 5 to the power 4, so I will multiply by 5 cube in the numerator and denominator. So 125, 5 cube is 125, 125 into 7 is 875 divided by 10 to the power 4. So we have to place decimal from the right hand side at after 4 places. So 0.0875. So we substituted 1 0 on the leftmost side of 875 to make it a 4-digit number. So we saw that all these fractions, all these rational numbers have a terminating decimal expansion. So what is the peculiar thing about these fractions is the prime factorization of the denominator have only 2's as in the case of 8, only 5's as in the case of 125, or a combination of 2 and 5 both. So this is not true for just these fractions, these are true for any fraction. On the basis of this, there is a theorem. So the theorem states that let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 to the power n times 5 to the power m, where n and m are non-negative integers, then x has a decimal expansion which terminates. Now let us move to the next thing, which is a combination of these both theorems. The next theorem is let x is equal to p by q, where p and q are co-primes, be a rational number such that the prime factorization of q is not of the form 2 to the power n times 5 to the power n, where n and m are non-negative integers, then x has a decimal expansion which is non-terminating repeating. So which is non-terminating repeating. So in the first theorem, we saw that if the decimal expansion is terminating, then we can write that decimal in the form of p by q, where the prime factorization of q is of the form 2 to the power n times 5 to the power n. And in the next theorem, we saw that if for a rational number p by q, if the prime factorization of q is of the form 2 to the power n times 5 to the power m, then the decimal expansion of that rational number will be terminating. And the third one is if the prime factorization of the denominator is not of the form 2 to the power n times 5 to the power m, where n m are non-negative integers, then its decimal expansion will be non-terminating repeating. So what we mean by non-terminating repeating is, let us see an example of this. Let us take the fraction 2 by 3. So here the prime factorization of the denominator is not of the form 2 to the power n times 5 to the power n. So if we want to find out the decimal expansion of this, we have to divide 2 by 3. So let us divide 2 by 3. So 2 is smaller, so we will put a decimal. So it will be 20. So 3 6 is 18. 20 minus 18 is 2. So we already have put decimal and there are no digits after 20. So we will put 1 0. So again 6, 18, 2, then again we can put 2, then 6, then 18. So it will go like this. So this is non-terminating, it is not ending because the denominator is not going to be 0 and it is repeating because the same digit 6 is coming again and again. So 0.666, we can put 3 dots after the rightmost digit. It shows that it is going till infinite, or we can put a bar sign over 6. So 2 by 3 is 0.6 bar, so 6 bar. So whenever the prime factorization of the denominator contains any digit other than 2 to the power n and 5 to the power n, so in that case the decimal expansion of the rational number will be non-terminating and repeating. Now based on the 3 theorems, let us try to solve the questions from exercise 1.4. So the question number 1 is, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. So from the previous theorems, we know that a rational number will have a terminating decimal expansion if the prime factorization of the denominator contains only 2's and 5's. And it will have a non-terminating decimal expansion if the denominator, prime factorization of the denominator contains any number other than 2's and 5's. So if I prime factorize the denominator here, so it will be 5 to the power 6. So it is containing only 5's, so it will be terminating. Now prime factorization of 8 is 2 cube, so it will be again terminating because it contains only 2's. And the prime factorization of 455 is 5 into 13 into 7. So the prime factorization of the denominator contains numbers which other than 2's and 5's, so it will be non-terminating. Now 1600 is 16 into 100, so 16 is 2 to the power 4 and 100 is 2 square into 5 square. So again the prime factorization of the denominator contains only 2's and 5's, so it will be terminating. Now 29 by 343, 29 by 343 is 7 cube. So the prime factorization of the denominator contains numbers other than 2's and 5's, so it will be non-terminating. Here the prime factorization is already given 2 cube into 5 square, so it will be terminating. Here the prime factorization contains 7, so it will be non-terminating. And 6 by 15, so 15 is 3 into 5. So just by looking at this, we see that there is a 3 in the denominator which is other than 2 and 5. But if we simplify it, so 3 will cancel out from the numerator, so it will be 2 over 5. And the denominator contains only 5, so it will be terminating. So remember here, we have to first simplify the numerator and denominator, then only we have to check the nature of the decimal expansion of the rational numbers. Now 35 by 50, again we can cancel 5 from the numerator and denominator, so it will be 5 7s are 35, and if we divide it will be 5 10s are 50, so 2 into 5. So again it has only 2's and 5's, so this will be terminating. Now here we can again cancel by 7, numerator and denominator, so 77 divided by 7 is 11 and it will be 30. So we can write it 30 is 2 into 3 into 5, but the denominator contains a number which is other than 2's and 5, so it will be non-terminating. So in this way we can find out the nature of the decimal expansion, whether it is terminating or non-terminating repeating, by the prime factorization of the denominator. Now question number 2, write down the decimal expansions of those rational numbers in the question 1 above which have a terminating decimal expansions. So which have a terminating decimal expansion. So in these cases we can make the denominator as a power of 10 to convert the rational number in the form of decimal. So we will do 1 or 2 questions just to give you an idea how we can do it. So let us try to convert the first problem, 13 by 3125, that is 5 to the power 6. Now to convert the denominator in the power of 10, I can multiply by 2 to the power 6 in the numerator and denominator. So 2 to the power 6 is 64. So 13 into 64 divided by, this will be 10 to the power 6. So 13 4s are 52, carry over 5, 13 6s are 78 and 5 83 by 10 to the power 6. So we have to place decimal from the right hand side after 6 digits. So 3 is already there, so 3 zeros we can put, and we can put a 0 decimal after these. So in this way we can convert the terminating rational numbers into their terminating decimal expansions. Just try to convert the denominator in the powers of 10 and put the decimal after those many digits from the right hand side. So similarly you can try the other ones. Now question number 3. The following real numbers have decimal expansions as given below. In each case decide whether they are rational or not. If they are rational and of the form p by q, what can you say about the prime factors of q? So here the first case is 43.123456789 and it is terminating because it is ending. So terminating means it will be a rational number and the prime factorization will be of the form 2 to the power n times 5 to the power n. Prime factors of q. So the denominator will be of the form 2 to the power n times 5 to the power n because it is terminating. In the case of second one, it is 0.120, 1200, 12000. So the number of zeros after every 12 is increasing. So this is non-terminating and non-repeating. So it will be irrational. It will not be rational because rational numbers can have decimal expansions only of the two types. Either they are terminating or they are non-terminating repeating. But here it is non-terminating and non-repeating also. So it will be irrational. Now in the case of third part, 43.123456789 and there is a bar means it is repeating again and again. So non-terminating repeating. So the decimal expansion, the prime factorization of the denominator will contain a number other than 2 and 5. So the prime factorization of the denominator, that is q, will contain a number other than 2 and 5. So in this way we completed the first chapter of the NCERT book, Mathematics Class 10. In the next video lecture, we will be covering important questions from the NCERT exemplar, R.D. Sharma and other horse questions. Till then, try to memorize the theorems, practice questions, whatever we have left from the exercises. In the next video lecture, we will be meeting with some interesting questions. If you liked the video, please like and subscribe it.